Let's review sections 10.1 and 10.3, which in your textbook are covered on pages 520 through 524 and 537 through 542. This video will be a little bit longer as we go through the descriptive statistics of two quantitative variables, so feel free to skip around as needed. If we need to plot two quantitative variables, we'll use a scatter plot, and there are four things we need to describe about a scatter plot. The form of the pattern, or what does the average pattern look like? Is it a straight line or is it non-linear? The direction of the scatter plot, meaning is it positive or negative, or as one variable increases, does the other appear to increase positive or decrease negative? Third, we'll discuss the strength of the relationship, or how clear is the pattern? How much do the individual points vary from the average pattern? And fourth, are there any outliers or unusual observations that do not seem to fit the overall pattern? For each of the following scatter plots, describe the form, direction, strength, and whether there are any outliers. Pause the video, then play for the solutions. The first scatter plot would be described as linear, showing a strong relationship, clearly positive, with no outliers. The upper right-hand point in this scatter plot would not be considered an outlier because it follows the general pattern of the rest of the data. The second plot would also be linear, a negative relationship though, and the strength would be moderate or weak because of this outlier. The rest of the pattern shows a fairly strong relationship, but this outlier makes the relationship appear much weaker. Finally, the third plot is non-linear, clearly positive and a strong relationship with no outliers. If you connected each of these dots, it would form a very slight curve. That's why we say the relationship is non-linear. Now focus on linear relationships for the rest of the video and for the rest of the class. So the following scatter plots are arranged from the strongest positive linear association on the left to those with virtually no association in the middle, all the way over to the right where we're showing a very strong negative linear association. Again, I can fit a straight line to each of these scatter plots. In the first three, we see that that line would be angled up or have a positive slope and therefore are considered a positive relationship. The right three scatter plots are angled down or a negative association, and the middle scatter plot is showing no association. Similarly, we see a very tight pattern indicating a strong relationship on the two outermost plots, but the middle plots are showing weaker relationships because the points are scattered more, or there's more variability in the observations. We will spend the rest of this chapter discussing linear relationships. If the scatter plot has a linear form, we can measure the strength and direction of the relationship using the correlation coefficient. Correlation coefficients are values between -1 and 1, where the sign of the correlation coefficient is indicating the direction of the relationship, and the magnitude of the correlation coefficient is indicating the strength of the linear relationship. Correlation coefficients close to 1 and -1 indicate strong relationships in those directions, and correlation coefficients close to 0 indicate no relationship. For each of the 7 scatter plots below, guess at the correlation coefficient. Pause the video, then play for the answers. How well did you do? Remember that the scatter plot on the left is showing a very strong, positive relationship, and so we would get a correlation coefficient close to 1. The scatter plot on the right is showing a strong negative relationship, and so we would get a correlation coefficient near -1 or -0.907. The scatter plot in the middle is showing almost no relationship, that is almost random scatter between the x and y variables, and so we would get a correlation coefficient near 0. The following graphic from Wikipedia summarizes some of the important characteristics about correlation coefficients. The first row is what we just discussed, that the correlation coefficient's value or magnitude is telling us about the strength of the linear relationship. The sign is telling us about the direction. The second row also shows us that the sign is telling us about direction, but it also shows that the correlation coefficient is not dependent on the slope of the line. While the slope and the correlation coefficient will have the same sign, their values are not related. Although not stated on this graphic, if the slope of the line fit is perfectly 0, as seen in the middle scatter plot, in the middle row, the correlation coefficient would also be 0. Finally, in the third row, we see that in a non-linear pattern, the correlation coefficient will be 0. If the form of a scatter plot is linear, we want to know the line of best fit for the data, which will be given by the equation y hat is equal to a plus bx. This is the same idea as your y equals mx plus b from middle school. We just have slightly new notation. Y hat is representing the predicted or estimated value of y for a given value of our x variable. X is a value of the explanatory variable, A is the y-intercept, and B is the slope. Finally, before we talk about lines a bit more, be sure that we are only predicting lines within our range of x's. Extrapolation is to predict a y value for an x value outside the range of our data. It assumes that what we are seeing in our data set extends beyond the values in our data, which can be a dangerous assumption to make. Lastly, we may ask you to find residuals, which is a vertical distance from a point to the line. In other words, it's an observed y value at a data point minus the predicted y value, or the estimated y value for that given x. Textbook, where we are looking at the diameter of a dinner plate and how that's changed over years. So our x variable or explanatory variable is years, and the y variable or response is the diameter of the dinner plate. And you are given this regression equation, negative 14.8 plus 0.0128 times year. Then to interpret slope, we would say a 1 unit increase in x, or for every 1 more year, it's associated with a slope 0.0128 inch increase, because the slope is positive, in the response variable, dinner plate diameter. To interpret the y-intercept, we would say dinner plates are estimated to be negative 14.8 inches in diameter in 0 year. Or the predicted y value is negative 14.8 if x is 0. Let's estimate a value. What is the estimated dinner plate size in 1990? Well, we can just take in 1990 and plug it in for year into our equation. And so we get an estimated dinner plate size of 10.672 inches. Well, in 1990, the dinner plate diameter was actually 10.375. How would we calculate the residual? Take that observed y value of 10.375 minus the predicted y value, which we just calculated, 10.672, to get negative 0.297 inches, or the dinner plate diameter in 1990 was 0.297 inches less than the predicted diameter. How can we pick our line of best fit? Well, the point is to minimize the residuals, or I want to get a line that has the points as close to it as possible. There are two ways that we could minimize those residuals. The first is called SSE, or the sum of squared errors, meaning we're going to square the residuals and then add them up. The second option is the absolute value and sum method, or SAE. Take the absolute value of the residuals and add them up. Why do I want to square them or take their absolute value? Because I need all the residuals to be positive. Points above the line have a positive residual, and points below the line would have a negative residual. And I need to make them all positive so that I can find the total distance from the line each point is. Lastly, we could ask you to calculate what's called the coefficient of determination, or notationally capital R squared. We can calculate R squared by taking our correlation coefficient, little r, and squaring it, or if we give you the sum of squared errors of a horizontal line at the mean response, or SSE y bar, and we give you the SSE of our actual line, you can use the formula seen to calculate coefficient of determination. The SSE of y bar is 3.51, and the SSE of the regression line is 2.23. Then the R squared value is 0.365, or 36.5%. How would we interpret that value? We would say 36.5% of the variability in Y, dinner plate sizes, is explained by changes in X, year. Make sure you have the summary measures of interest down and the notation for each. So the two summary measures we'll look at for linear relationships are the correlation coefficient and the slope. The parameter notation for correlation coefficient is rho, and the parameter notation for slope is beta. The statistic notation for the correlation coefficient is r, and the statistic notation for slope is b.